Hello everyone. So I just wanted to make a quick video going through an example of how machine learning can be used in the context of material science and why that would be beneficial to use. To give a bit of background, currently the two most common ways of learning the properties of materials are by conducting physical experiments and simulated experiments, the latter being somewhat faster and more cost effective, albeit still slow. So calculating new material properties is actually incredibly slow, and that's not accounting for the thousands of possible materials that we simply cannot calculate. Disordered structures, F electrons, things we simply cannot quantify with the knowledge and technology that we have. So this is where machine learning comes in. What machine learning allows us to do is to rapidly predict material properties. Sure, those predictions give up some form of accuracy, but that also means we can screen for possible materials at a much faster rate. Think like 1 minute as opposed to days or even weeks. So the idea is once you have a model working, you can make predictions with it, and if it looks interesting, you have some sort of verification or incentive to go after it. This makes the process of identifying good material candidates a lot easier. With that being said, in today's video, I'll be showing you the basics of setting up a model that predicts the critical temperature of superconductivity. And once I'm done with the model, I'll be comparing its predictions to the actual data provided. Anyways, I think that's good enough as an introduction, so let's get started here. I'll be using the superconductivity machine learning dataset provided by UC Irvine. I'll just go through the steps of downloading it first. The link will be provided in the description. So we are given a zip file here. Yeah, okay. Okay, so there are two separate CSVs. For those that are unaware, CSV basically stands for comma separated values, and it's a machine-friendly format that allows us to read and separate values into rows and columns. So I'll just start off by extracting this. And I'll be extracting it to my desktop. Okay, so before we get started with the actual coding, I just want to take a look at the format of the given data just to get a feel of what I'm working with. So while we are waiting for the Excel file to load, I'll just take a look at the data set description on the website. So it says here we are given 81 features, yada yada. Critical temperatures are a variable of interest. The second Excel file contains the chemical formulas for the superconductor. Okay. So now that they're both finished loading, I'll just browse through it. Okay, so here's our critical temperature. So let me just note down the name of the cell. And let's just go to our unique Excel file. Sorry about that. Okay. Okay, so at first glance, there are two things that I notice. One, both files contain critical temperature as a column, so there's a bit of redundancy there. I'm planning on concatenating both files together so it's easier to work with. So I'm probably going to drop one of those columns when I'm preparing the data. Actually, the chemical formula is also kind of pointless here, at least for what I'm planning to do. Normally what you could do is read the column with a library like PyMagin to generate properties that you can use. But since we're given enough features here, I can just drop this one as well. Okay, so now we can finally get started with the code. I'll be using Python to run this, and I'm assuming you're all familiar with the language. If you're not, that's fine. I'll be explaining my thought process while I'm writing. So, yeah, I'll be explaining it in a way that won't be too difficult for you guys to follow. The environment I'll be working in is Google Colab, mostly because it skips the hurdles and pain that you have to go through with installing and initializing the packages. So you can just copy what I write, or actually, yeah, even better, I'll just link the code in the description. So if you're feeling lazy, or if you don't do well multitasking, you can just follow along with the notebook. Actually, before we get started, I almost forgot something very important. I should explain why machine learning is necessary in this scenario with what we are doing. So superconductors is a pretty new field. It's only like a century old. And to my understanding, the connection between the characteristics of superconductors and chemical properties is still poorly understood. So going back to what I said earlier, instead of calculating these properties, what we will be doing here in this video is predicting them instead. And I think 21,000 data points should be enough to arrive at a reasonably accurate value. And just to give a bit of more background, superconductors, for those that are not aware of it, superconductors are essentially those materials that have zero resistance to electron flow. So the critical temperature here is the temperature that allows them to behave that way. I won't get into the physics of it, but when the temperature is below that of the critical temperature, the electrons become coherent and end up creating those powerful magnetic fields, which can see applications in things like hadron colliders and particle accelerators. So yeah, that's anyways, that's enough rambling for me. To get started, we want to first import the libraries necessary to model the data. I'll give a brief overview of each one, but you'll see why we need them as we go through the code. So first things first, we want to upload pandas as PD. So what pandas allows us to do is it creates data frames to simplify data processing for us. Next thing, we want to import Seaborn as SNS. So Seaborn allows us to visualize the data during processing, just to verify and make sure that everything's going well. Next thing we want to do is import NumPy as NP. So NumPy, I'm going to be using it to handle things like arrays and matrices. It makes life a lot easier for me. And I think, yeah, finally, we're going to import matplotlib .pyplot as PLT. So what I'm going to be using this for is to visualize the model performance once I'm done with it. Okay, so now that we're done with that, we want to first start off with uploading our training files. So from google.colab, import files, and I'm going to do it twice. Uploaded files equals to files.upload. So what this does is it essentially asks for an input, like a file input. So if I run it here, oh wait, I should probably run this first. Okay, yeah. So what it does here is it asks for a file input. So we're just gonna choose our train file first. Okay, now the uploading takes a bit of time, so I'll just fast forward this part. Okay, so now that it's done uploading, the first thing we want to do, and this is pretty universal with all sorts of machine learning applications, is verify that our data was read correctly. So since we are given two data sets, I'll be storing each data set into a single variable and concatenate them. So store the data into variables. I'll call them dataset 1 and dataset 2 for now. So dataset 1 equals to pd.read csv train.csv, and for our dataset 2, it's going to be the exact same thing, except for the fact that except for the fact that I'll have to drop both the chemical formula and the critical temperature from this training set, so I don't end up with redundant columns. So drop critical temp, I think that's how it was spelled, and the other one was material. Okay, so now that we are done with that, I can use the panda concatenate function to concatenate them in terms of columns. So I'll be calling it data frame equals to pd.concat data set 1 data set 2 and I'll set my axis to 1 here also. So this basically tells pandas that it tells pandas that I want to do it in terms of columns. So now that we are done with that, I'm going to output the data to see what it looks like and verify that nothing has went wrong so far. So I'll only output the first few rows. So 5 should do data frame dot head. So this is just to save processing time. Okay, so now let's run this. Okay, so from the looks of it, things are going well for now. Next thing I want to do is check if there are any missing or null values, just to see if I have to deal with those as well. So data frame dot is null dot values dot any. Okay, false. So I'll just I'll just check the shape of the data. Okay, data frame dot shape. Okay, so we have 168 features here. So everything seems to be going well. Normally you can move directly into the machine learning portion, but I want to first filter my data. So there are 168 different columns for 22,000 data points. That's very taxing on both the memory and disk space and processing speed. So I'll just be cleaning my data first before moving on to that part. To start off, we should first set up a criteria for what features to drop. Well, off the top of my head, I can think of removing any mutually correlated features. We don't really need multiple features telling us the same thing. We should also get rid of remove values with low variance, as values that rarely change with different materials don't really tell us much. And finally, we should probably get rid of any features that have a low correlation with our critical temperature. Okay, so I'll just fast forward this part and explain my code once I'm done. Okay, so we're back. I have decided not to filter out the values that are not correlated with the critical temperature, because even if it barely has a correlation, a nonlinear model might find something that I can't see. So unlike the other two where one has redundant information and the other barely has any relationship, this one is a bit more ambiguous and has some value to it, so I'll just keep it. Okay, to get started, I'll first explain how I filtered out the mutually correlated features. So I first declared a variable called correlation matrix and set it as the correlation matrix. So just to give you an idea of what the correlation matrix looks like, I'll just data frame.core. Okay, so once I run this, it'll just give me back a table with the correlation that each feature has with one another, and that's about it. So I then declared a set and named it correlation features. And I will use this to store the names of all the correlated features that I have. Now what I did here was that I wrote a nested loop that will go through all the columns in the correlation matrix and add columns that are not the critical temperature and have an absolute correlation value that is above 0.75 to the correlated features set, which I will then use to remove from the data set. So as you can see, running it shaved off about 60 features. So next, with removing values with low variance, I'm using a feature selection algorithm from sklearn to remove all low variance features. So here I started off with a threshold of 0.1, which means it will remove all features with a variance below 0.1. Then I fit the data I initialized earlier into this filter, and only the ones that pass through this condition remain. And the ones that remain, I use those to transform. I transformed it to drop those features that fail to pass through, and this filter drops our number by another 40. So now it's at 63 features. Okay, so now that I'm done with now that I am done with that, I'm just gonna call a new code, and let me just delete this first. Yeah, I'm just going to basically copy this into a new file. So I'm gonna call it .c data frame.cs .2 underscore CSV. I'm gonna call it clean data.csv. Okay, so what I did here was that I copied all the data in our variable into a new file, and I'll be using this file too for my machine learning part. Okay, so now that we're done with initializing and we have cleaned our data, we can start the machine learning. We can start with the machine learning. So the algorithm that I'll be using for this is called random forests. I'll try my best to explain what it is. If you find anything confusing, just comment down below and I'll see if I can clear up any confusion. So random forests is an ensemble machine learning technique. In other words, it uses multiple algorithms to obtain an overall better prediction. In this case, the learning algorithms are a series of decision trees. So you kind of get you kind of see where I'm getting at, right? So the random portion of the name comes from the decision trees, each taking a random sample space from the training data. So what you end up having is this forest of decision trees, each with its own random data set, combined together to arrive at a prediction which would be closer to the true value. So individually, individually those decision trees are riddled with errors. They're not going to be accurate. So they're going to have a high variance and high bias towards the sample space that they've been given. But once you're combining all of them together, these biases, these errors are reduced. The way that I like to think of it is you're given 10 bad models, each with random errors, but combining them together, the errors will average out to 0 since they're random. That's the idea behind random forests, at least. So I'll be using it because it's a pretty robust algorithm that pretty much consistently produces reliable results and also reduces overfitting in data, which I want. So the idea is also pretty simple, but the training time might take slightly longer. It should be fine since we're only given 21,000 data points though. So I'll do the same thing I did last part and finish writing my code first, and I'll explain it afterwards. Okay. So what I did here was I first imported the necessary packages. So to start off from top to bottom, random forest regressor is the algorithm I explained earlier. The train test split function allows me to divide my data into training data and testing data. Here I just called a few metric libraries to get an evaluation of how my fit would be like compared to my actual data. And finally, I called the standard scaler, and I'm using that to transform my data such that its distribution has a mean value of 0 and a standard deviation of 1. So my reasoning for doing this is because our data has been measured on different scales. As a result, each feature will have a different contribution to when model fitting. So doing this allows me to prevent any bias from occurring in my model as a potential problem. Okay, so to start off with, I set my standard scaler as SC because I don't want to call standard scaler. I'd much rather just type SC instead. So here what I did was I read the clean data file that I created earlier. So my independent variable will be the features collected, and my dependent variable will be the critical temperature of the superconductor. So going back to what I said earlier about the standard scaler, I'll be using it on my features so that each feature has an equal contribution to the model. So, and that's what I did here. I dropped the critical temperature from my x-axis and I scaled it with the standard scaler. And then here what I did was I added the scaled values into I basically rewrote my columns as my scaled values. And then finally I set my critical temperature as my y-axis. So what I did here was I used the train test split function that I called earlier to split my data into training and testing data. So here I set it to 25% testing data, and I'm going to train it on the remaining 75% of my data. Random state is it's like a pseudo, it's basically a it's not really random, it's pseudo random. So what I'm doing here is I set it to 42, so as long as you type 42 in, it will split the testing and training data to be exactly the same as what I get here. So your results should be pretty much the same here. So After that, I initialize the random forest regressor to a variable called forest. I set my number of trees to 200, and my max features is set on auto. This parameter basically will simply take all the features without any restriction for every tree. So now that I'm done with this, I then fit my data into my model, and now I can use the pandas series function to store my model's critical temperature predictions into an array. So yeah, I think that's about it. We can now evaluate them on the basis of the R-squared and RMSE, and here I output the values, and they turned out to be they turned out to be pretty solid considering the amount of feature engineering that went into this model. So let's just get a better idea of how accurate the model is by graphing our predictions against the actual result in Matplotlib. So like what I did earlier, I'll fast forward this part. Okay, so based on the spread, I think we did a pretty good job modeling the data. So what this does is it saves a lot of time if you want to introduce new samples to predict how they will perform and use that as a precursor to decide on whether you want to pursue it or not. So overall, from what you can see, this doesn't really take that long, but that is assuming that you know exactly which model to use, what property to look at, which direction you want to take with the model. I've simplified the model a lot. I've simplified the method a lot, but in reality, you can do a lot of feature engineering to cater your model towards what you want, and that's going to take a lot more time. So this is a pretty good alternative as opposed to outright conducting experiments and simulations, which could take sometimes anywhere between weeks or months to prepare for. So yeah, if you have any questions, I'll try my best to attend to them. So yeah, see ya.